All right, 3-3, we're going to be starting to look at some logarithmic functions and logarithms. And to get there, we're going to take what we did in 3-2, which was looking at exponential functions. How do we create a logarithmic function from an exponential function? Then we will take a look at common and natural logarithms. And then we're going to finish off by looking at the graphs of the logarithmic functions. So logarithms is something that you were first introduced to in Algebra 2. And so now we're going to add to that and look at what else can we do with these logarithms. So first of all, where does a logarithm come from? It is the inverse to a exponential function. So here when I look at my graph that I have and y equals b to the power of x, well, what if we had to solve for x? So what if we knew with our last examples that we were doing, we wanted to figure out in what year did the Lazy Days Island, in what year did it reach 5 million people? Well, what you're trying to do then here is you're trying to solve for the variable of x. And how we can do that is through a bunch of guess and check, or we can have some exact measures of it using logarithms. And we are working with then the inverse of that because we're solving for x. So talking about inverse functions, remember that we flip our values of x and y. We change those out. And now solving. How we solve, and we'll be getting over into this in the next couple of days, is how I get this y out of the exponent is by taking what we call the logarithm of both sides of our equation. So I'm going to take the log of x and the log of b to the power of y. And using our power property that we'll look at again in a couple days, because we'll be doing those solving then, we get log of x is equal to y times the log of b. And I can now divide both sides of my equation by the log. Oh, sorry. Fix this. So I'm going to divide by the log of b. And I end up with y is now equal to the log of x divided by the log of b, which we will end up talking about how this is the same thing as log base b of x. And so this is where our logarithm comes in. When we start talking about the graph of a logarithm, it's the inverse is a reflection over our line of y equals x. And as I reflect this line over here, which was a y-intercept at our value of a, or in our case here 1, now we're going to reflect this over that line, and we are going to end up with a x-intercept at 1. Our horizontal asymptote, which was your x-axis, is now going to be our y-axis. So everything is changing positions. So looking at our logarithms, it's nothing to be afraid of. And a lot of times people get all scared when it comes to logarithms, but realize that all you're doing is you're solving for the exponent on a power function. So if I gave you problems like this, I think you'd be very successful in solving for them, especially.
Thank everyone for a great day. Please get out of here and have a great long weekend. We'll see you on Monday.
All right, so as you look at this here, when you look at the problems, we're trying to solve for x. And so looking at it, 6 to what power gives you 36? Using the little chart that I have here, which I have up in the classroom as well, if I look at 6 here, 6 to what power equals 36, we know that x is going to equal 2. 4 to what power equals 256? Well, that's x equals 4. 8 to what power gives you 512? That's x equals 3. So if you can do problems like this, you can solve logarithms. Now, some more challenging problems that you can look at that we'll be looking at also is using this chart to try and come up with, well, 25 to what power equals 5? Well, here we're looking at x is equal to 1/2. 1/2 being the square root, because when we take the square root of 25, I get 5. 3 to what power equals 1/3? Here we're talking about x is equal to 1/3. So we're using all of these powers that, calculating the powers that we did the other day, trying to use these in different ways. Now, I understand that not all logarithms can be done in our head. We do need to do some on our calculators, but here it's just showing you that all you're doing is solving for the exponent. So here's where you're at. If we have this is our exponential notation, so b to the power of y equals x, and then here's our logarithm notation. So what's happening here is you have this base of your power. Well, that base is going to become the base of your logarithm. It's going to be that subscript that gets tackled onto your log here. And because when you're solving for logarithms, you're solving for the exponent, which is our y. This is why we have our logarithm here equal to y. And then lastly, this value of x here, that's what we're going to take the logarithm of. So to show you how to go from exponential form to logarithmic form, I have 7 to the power of 2 equals 49. Well, the base is going to be 7. The exponent here is 2. And then you have it's equal to 49. So what this is going to look like is we're going to take the log of base 7 of 49 equals 2. Notice that it equals the exponent. The next one here, 3 to the 4th power equals 81. So we're talking about the log with a base of 3 of 81 equals 4. So again, it's equal to that exponent because that's what we're doing when we solve logarithms. And the last one here, I have a base of 256. So log with a base of 256 of 4 is equal to 1/3. So we're just going here from exponential form into logarithmic form. Makes it a little easier to solve. So when you're trying to solve logarithms, when you see log base 2 of 8, you're like, oh my gosh, what do I do? Well, just like here, how we can take a exponential or a power function here, exponential function, put it into a logarithmic function, we're going to do the reverse. We can go from logarithmic to exponential to make it a little bit easier on you. So here, when I look at this problem, log base 2 of 8 equals x, think of it as 2 to the power of x equals 8. And so when I look at 2 to what power gives me 8, that's telling me that x is equal to 3. Log base 5 of 625, 5 to what power is equal to 625? So 5 to the 4th power gives me 625. So here x is equal to 4. Now, when you look at solving these logarithms, these are all logarithms that we can use based off of the chart that I have in the room or that I'll be giving to you. Not every single number is on there. And so then we are going to have to resort to using our calculator. However, your calculator, at least the older calculators, only know how to calculate 2 types of logarithms. And they know how to calculate the common logarithm, which is a logarithm of base 10, or they know how to do a natural logarithm, which is a logarithm of base e. Well, slight problem with all of this, and that is the fact that not every logarithm, as we see right here, has a base 10 or has a base e. And so we'll be looking at how you solve those down the road. But how to use your calculator to evaluate some. If you have a log base 10 of x, oftentimes they will not put the base in the problem, so you'll just see log of x, just like I have here of log of 34.5. So I'm looking at 10 to what power gives you 34.5, which off the top of our head or using the chart that I have in class, you're not going to know that. So instead, we go to our calculator and we plug in log of 34.5, hit enter, and there we go, I'll round that up to 1.54. If I wanted to take the log of 0.43, we end up with a negative 3.7. Sorry, negative 0.37. And then if I go ahead and I take the log of negative 3, I get an error. It says non-real answer. Well, why is that? Okay, why do I not get an answer for the logarithm of negative 3? I'm saying here that 10 to what power gives me negative 3. Well, here's the thing. With logarithms, when you have a base of 10, 10 to any power will never give me negative 3. The only time that would ever work here is if I maybe had a negative 10 to the power of x, okay? But here we're working with a base 10. Logarithms here will not, we cannot take the logarithm of a negative number. It just does not work. Thinking back to what the graph of this is, your domain of your logarithm here is all real numbers that are greater than 0. We do not have any negative values. So we cannot take the logarithm of a negative answer. It's just not possible. So there's our logarithm of base 10. Now I'm going to take a look at what the logarithm of a base e looks like, and that is known as our natural logarithm. As we start talking about continuous growth and continuous decay, this is where our natural logarithm is going to come in. So where you can find the natural logarithm is right under your log button. So if I take the natural log of e, which I'm going to hit second and then divide here, and when I plug that in, I end up with 1, which here, if you think about it, e is my base. E to what power equals e, so we're going to get 1. If I take the natural log of 23.5, we get 3.16. And then if I take the natural log of 0.48, oops, we end up with negative 0.73. And there's our ways of calculating these on our calculator. What we're going to be focusing on these first couple days is trying to evaluate logarithms using our chart that we're going to be using in class, because we're going to be working with solving these logarithms without using a calculator for some time. But then eventually we will need to use our calculator once we start looking at applications. Finally, I want to finish up by looking at the graphs of logarithmic functions. So we talked about how it is the inverse of an exponential function. And with the two functions, they look really much practically identical to each other, log base b or a natural log. And really just everything ends up at the rate at which it's going. But both of these here are going to have a x-intercept at positive 1. When you take the logarithm of 1, you will always end up with 0. So when I take log of 1, what ends up happening here is I'm saying 10 to what power equals 1? Well, that's when x is equal to 0. Here, e to what power equals 1? That's going to be when x equals 0. So a logarithmic function, as long as there's no transformations taking place, we are going to have an x-intercept or a 0 at positive 1. We have asymptotes, which are going to be along our y-axis, which is the opposite of when you're looking at exponential growth. And both of these graphs are going to be increasing on the domain of x being greater than 0. So with our functions here, with our domain being x is greater than 0, and then we have a range of all real numbers. So this is our first day of the introduction of logarithms. If you have any questions, let me know. Otherwise, we'll be practicing all of this in class over the next couple days.